Welcome to today's FDTD Go 16 Applications webinar. Chad is going to be with us today to talk about the Day Cloud Phase Distinction RGB composite, and he'll be looking at gaining situational awareness for DSS. Our presenter is Chad Gravel from the NWS Operations Proving Ground, and in 2 hours he'll be also having another webinar talking about the GLM data in AWIPS. First, we'll talk a little bit about if you're unable to attend today's live webinar. Just a reminder, all of these are recorded and placed on the Visit web pages available at our URL that's shown here. Also, if you're interested in leading one of these in the future, just let myself, Dan Bicus, or Scott Lindstrom know. Next. Just to go over a little bit of a webinar protocol, we have about 20 minutes for our speaker. You can either send the questions via the GoToChat, or there will be a Q&A period over the phone once Chad is done speaking. We'll be done by 17:30, and remember, do not press hold and mute your phone when you're not speaking. So without further ado, I'll turn it over to Chad.
All right, thanks, Dan. I'm going to jump right in because of that 20-minute time, but today I'm going to be talking about using the Day Cloud Phase Distinction RGB to gain situational awareness for DSS. And most of you have probably, seen this RGB or used it in operations. It's actually pretty complex. There are, eight different items that I have on interpreting this RGB. Anything from low clouds up to thick upper-level ice clouds. But in reality, this is actually a simple RGB because there are no differences in the RGB components. So what we have is the 10.3 clean IR in the red, the green component is the red visible, 0.64, and the blue component is the 1.6, the snow ice band. But you can see that it's pretty complex. But what I'm going to be talking about today is just the transition between low-level liquid clouds and glaciating clouds here in olive color. So the first thing I thought I would do is I would break down the RGB. So let me kind of show everybody what I have here. So in the top left panel, I have the RGB, the Day Cloud Phase RGB. And then I have each component. So the red component, clean IR, is in the top right. The units that you'll see are brightness temperatures. On the bottom left, I have the green component. That's 0.64. The sampling is reflectance. And then the blue component, the snow ice band, again, sampling is a percent of reflectance. So the first thing that I have hovered over is a very, very shallow cumulus cloud. And that's basically in this teal color. And that color comes about because we have a pretty good contribution of green and blue, but really no contribution from red because it's a very warm cloud. But if I move forward and then same time, and then I just hover over a little deeper cumulus, you can see how the color changes to more of an aqua color. So that I'm calling deep cumulus. So there's, again, very high contributions of green and blue. You can see that those colors are almost maxed out. And now we're starting to get a little bit of red contribution. But you can see how the color changes just by doubling the green and blue components of this RGB. So now we're going to move forward a few minutes, and now we're going to hover over more like a towering cumulus cloud. Okay, and you can see that right there. And
webinar.
Say that again?
The Day Cloud Physics RGB.
Someone's not muted. Please mute your phone. Thanks. But again, really high components of green and blue, and now we're starting to get a little more red contribution. That's almost up to a quarter of saturating the red color because we have a cooler brightness temperature on the top of that towering cumulus cloud. And you can see how the color starts to get a little more green, almost like an aquamarine color associated with that. And then if we move ahead even further, now you can see that the top of that tower is more like olive. So now, once we get more of a towering cumulus that's almost a mixed phase cloud. Now the reflectance of the blue drops because there's ice particles, small ones, at the top of the cloud. There's still a pretty good green component on a highly reflective cumulus cloud. And then obviously the clean IR is really starting to cool, so you have much more red contribution. And you can see how those color changes. And if you kind of take a look at them, it may be subtle, but if you take a look at those colors next to each other, you could potentially get some information out that would be useful to the forecaster. So why am I bringing this up for DSS? And the reason is lightning is bad when you have a lot of people outside potentially. So these long flashes that occur sometimes lead to cloud-to-ground stroke. So can we use this RGB to potentially predict the onset of in-cloud or intra-cloud lightning and then cloud-to-ground strokes as well? So now we're going to take a look at look at a time sequence of how this one tower in particular starts to change and evolve. So I have images up here every 5 minutes, and you can see we start at 16:02 on this day. I think it was March 5th. More in this towering cumulus color. But you can see things transition every 5 minutes pretty quickly, and by 16:17, we start to get that olive color, and by 16:22, the top of that Q has many ice particles, which is why we get a really good olive color associated with that. So now let's add a few more times. We're going to add 10 more minutes. And again, you can see how that Q evolves. And you know, the reason why this is important is because as ice crystals begin to form in the cloud within an overabundance of supercooled water droplets, grapple develops that collides with ice crystals, and in time you end up with opposite polarity. So ice crystals usually have a positive polarity and grapple is usually negative. But because these are different sizes and have different fall velocities, and we have an updraft sending these smaller particles to the top of the cloud, it allows for separation after this collision. And what ends up happening is when the electrical forces in the cloud between those two charge centers is high enough, lightning occurs. And you can see 5 minutes later at 16:37, we had our first intra-cloud lightning stroke. And this is from the Earth Network's total lightning. So if we see how that evolves, now we're moving forward every minute. So 16:38, there was no in-cloud lightning. 16:39, there was more in-cloud lightning, same at 16:40. And then if you look at 16:41, now you have enough charge separation, enough grapple in the middle of the cloud where you all of a sudden you get a cloud-to-ground strokes. In this case, there was actually two. So if you go back to 1622, and you can say, okay, I really think this towering Q is developing. It has ice crystals because it has changed color. It's now this, at the top of the Q, it's now this olive color. You can see that there was pretty good lead time on the cloud-to-ground stroke. So that's kind of the focus here. So now let's take that concept, okay, and what we just looked at within this RGB, this very specific application, and now we're going to apply it to a very hypothetical situation. This did not occur, but I'm just trying to give everybody a taste of how you could potentially use this in real time. So here's a 4-panel, red viz top left, clean IR top right, the RGB is in the bottom left, and then I have the KJAX, high-res reflectivity on the lowest tilt on the bottom right. And you see we have a DSS event. We're going to call it the Wayne County Fair. And the local emergency manager would like 30-minute lead time on when lightning would occur within 5 miles of the fair. So you could be at the office, you could be on site, but you're supposed to obviously monitor, for this partner, the local Wayne County emergency manager. So that's kind of the setup here. And then the red ring is my 5-mile radius. So we're going to move forward every 5 minutes. And one of the things I'd like to point out is to the southwest of this event, we have developing Q, and we have towering Q, and now we have some showers starting to develop. By 1848, you can see this is, more showers. Still, there are there is no lightning yet. 1853, same thing. And 1858, you can see now we have this Q field. We start to get a couple in cloud and CGs to the southwest. But if you think about this boundary, now we can track this boundary moving to the northeast to the DSS event. And one of the great things you can use is obviously the time of arrival tool, and you can just try to time out how this queue is evolving. It's obviously moving to the northeast at a pretty constant rate. And if you use the time of arrival tool with just the data I just showed you, it basically gives a prediction of within 5 miles, the leading edge of that Q field, that developing Q field, would be about 2030 Z. So I'd like everybody to remember that. So 30-minute lead time on quote-unquote lightning within 5 miles of the fair is around 20 UTC then. So we want that 30-minute lead time. So now we're going to jump ahead. 1917, you can still see we have, developing Q. We move about 15 minutes ahead, 1932. Now, within the leading edge of that Q, we have our first in-cloud lightning with showers approaching the DSS event, obviously the outdoor fair. We move forward. Now, this is 20Z. This is the time that we need to be confident enough to tell the emergency manager, will there be lightning within 30 minutes? And you can see how all these towers start to turn this olive and yellow color out ahead of that line. We jump ahead to 2027, so almost 30 minutes before, lightning is getting very close within that 5 miles. And then at 2032, you had your first in-cloud lightning within 5 miles of the event. And then at 2033, 1 minute later, you had your first cloud-to-ground lightning stroke. So obviously, this did not happen. It's a hypothetical example, but I'd like to try to give everybody, without going through the RGB, just trying to apply it as well. And just to start to get everybody thinking about how you could potentially use that. So let's look at a little more recent event, and we're going to give you some GLM data. This is a little precursor to what I'm going to be talking about in a couple hours at 19Z. So let's take a look at the same thing, but from a perspective of GLM. So before I was showing Earth networks. So we're going to look at this one little storm in southwestern Georgia. You can see it's already a towering Q. There's already ice at the top of that Q. It's already turning that olive yellow color. And now we're going to take a look. So we're looking at images every minute here now. And I know it might be hard to see, but you can see there's some in-cloud flashes that GLM is showing. And if you look at 1743 that I'm circling with my mouse, you can see that there's pretty good in-cloud lightning now, about 4 to 5 flashes over the last minute. And you can see the footprint of the GLM flash is there in this flash extent density product. And by 1746, still in-cloud lightning. There's no CGs yet. So, but on the next minute at 1747, you can see there was 2 CGs. So as you see this developing Q, you see how ice crystals start to get separated from grapple potentially in the middle of the updraft. That GOES 16 is sensitive enough to see this. You can see in this example, there was about 10 minutes of lead time. And actually, the signal was there before 1737, but I just showed you that last 10 minutes. And it's, again, this is a very recent example. This is from basically 2 days ago. It happens quite a bit. The only thing that I would caution, and I have this on my last slide, is that you should be careful about using it in the cool season potentially and near sunrise and sunset, because the RGB can potentially change color a little bit by that lower sun angle.
Okay.
So just, I'd like to wrap up, at least a couple minutes early, because I'm sure there's going to be questions out there. But without exploiting the GOES 16 1.6 band, basically the snow ice band, this capability is not possible. So it wasn't possible in previous generations of GOES. And this proof of concept that I showed is obviously a hypothetical example of how the RGB could be used to provide DSS when convection is expected to impact an outdoor event. But there's a lot of applications for this. So how else could we potentially use it? For example, the Jacksonville WFO is investigating using this RGB and how signals in the RGB can allow their forecasters on their DSS shifts to send out targeted messaging tweets, alerting the media and the public before cloud-to-ground lightning is occurring. So it's not only just for an outdoor event. You could potentially, send out targeted tweets if you're expecting a lot of people outside for some reason or another. Obviously, in Florida, there's many people outdoors at all times of the year, and many people lose their lives to lightning in Florida more than any other state. So this is very important to, obviously, those WFOs. And really, this RGB is allowing the Jacksonville office to try to deliver better service. And the results of this experiment that they're doing for Seabreeze convection this summer will be presented at the NWA annual meeting in August. So those are just kind of the things that you could potentially do with this RGB. As I said, the RGB should be used with caution in the cool season. I've seen examples where you get this olive yellow color at the top of convection in February time period and in early March, where you get very little lightning just because of how cool the atmosphere is. And then the very last thing, I'd like to obviously thank Jason Goslin, who's a forecaster at the St. Louis Forecast Office. He actually was one of the first that showed me this concept. He was using a different RGB. It was the daytime composite number 1 RGB. And I really think the day cloud phase does a little better job of transitioning between very shallow liquid Q and mixed phased towering cumulus. And then lastly, to a handful of the Jacksonville WFO forecast staff for providing me the opportunity to really introduce this concept with them when I was down in Florida for Go 17 launch. So with that, I would love to take any questions. I think I'm on a couple minutes early, and I'm hoping there are some out there.
Chad, this is Rosald at Eastern Region SSD. I think this is terrific. All that we can do to apply, what you're showing at the beginning is especially important to the field. One suggestion, I had trouble following this because of the small black cursor. So I really got lost. So if in the future you can annotate, with yellow or what have you, I think that'll go a long way toward, being able to follow along and have the best value of this presentation, because you've obviously put a lot of work into it.
Thanks for those comments. I appreciate it.
Chad, when you actually sample the RGB image itself, if you did some sampling, what does it actually display?
It actually displays, let me go back and I can kind of give you an example. It actually displays these values here in the top left. So at least currently. So you'll get a readout of the red, green, blue component, and then you'll get a number out of 255, and that's basically where that color falls on the 0 to 255 color scale. And then next to that, you'll get the percentage. So, if you do, obviously simple division, 119 over 255, you'll get 47%, which means the red component is 47% saturated. And that's from that, that negative 21 Celsius of the clean IR. And that, it kind of gets tricky, and that's why I put these ranges here next to each component, because anything warmer than 7.5 C is 0, and anything cooler than negative 53.5 C would be 100%. So the value here in the clean IR basically governs, the percentage of that red component there, and it goes the same for the green and the blue as well. Does that help?
Yeah, I just find that curious, because I think knowing those values, we could almost set up a little, localized algorithm to sort of monitor for that, if that makes sense. I know it would be heavily dependent and would need a lot of testing and things, but I was trying to think of something that we could use sort of as an alert kind of status for these DSS events, if in case, you get to a point where you're trying to monitor, dozens of them or something.
Yeah, absolutely. And down where you guys get, summer convection, like, you have QL quads, and, some of the towers may be, growing, and, and you can kind of pick out areas. It's just, I've looked at this quite a bit over the last, 2 to 3 months on numerous cases, and it's amazing how well it does, picking out these towers. And if you look at Viz on the bottom left in this just one image here, it's kind of difficult to see which towers are going to grow. And the snow ice band is just so sensitive, and it's just nice, and it kind of, it picks out these almost quote unquote hot zones, for lack of a better word. And yeah, I mean, and just to kind of, I didn't show this, but obviously this one does the same thing that that I have my cursor near right here, and then other areas end up also, having this olive color to them, signifying a towering mixed cumulus cloud. But yeah, I think that would be something interesting to, to work on for sure.
Yeah, Chad, this is Frank Alzheimer. Wondering if you have any idea on the roughly what the false alarm rate would be on these, because that would be important in the consideration of using it for IDSS.
Yeah, and obviously it's tricky, right? This is a great project for a grad student, right? To just find a bunch of cases and really and storms, and really go through and kind of document how this RGB changed. But one thing I can tell you is you can get the signal. Like for example, I'm looking at this tower here, and you can see this olive to yellowish color here, and you can get the signal. But if the Q doesn't continue to grow, basically your threat of lightning decreases. And I've seen that example where you kind of get that, but you can visually see that either it got sheared off, or it just there was the vertical development of that tower just ended, or that developing shower, and then it didn't. Obviously that threat went away. So I have seen that. So I mean, you got to be smart. So luckily with imagery every minute and every 5, you can kind of see that. So there can be, but it's honestly I probably wouldn't have put this together unless I was pretty confident. And when these storms continue to develop and you have the threat of convection, it honestly does a pretty good job. So I would encourage you guys in the later in the summer, when you get ordinary convection for sure, to really take a look at it and get some eyes on it. Obviously, as I said, I've only been looking at this for 2 to 3 months or so, but I've been pretty impressed, and I've seen it on a bunch of different cases.
Yeah, thanks. And I realize that you're not going to have any specific numbers or anything, but I just wanted to get your feel, because you have been looking at it more frequently, probably.
Yeah, I mean,
as most of us.
Like if this storm developed, continued to develop, and this one to the northeast didn't, there probably wouldn't be lightning, because you're getting this signal because of those really small particles, really, quite a bit early, 5-10 minutes at times, even before. And some of the examples I showed were 15 to 20 minutes. So, but if that updraft doesn't keep developing, you're just not going to get that charge separation to continue, and the threat of lightning is obviously lower.
Yeah, thanks.
Hi, Chad. It's Scott. Thanks. This was fun. I'm kind of curious what this would work. how this would work if you just looked at the split snow difference, which isn't working yet, but should be sometime soon. Because that'd just be the 1.6 minus the point, and you wouldn't have to deal with, a convective example in February when the temperatures at the top aren't cold.
Sure. I don't know. I think we should look at it for sure. And maybe you put this in a 4-panel. You put that split difference in a 4-panel with the RGB and in the red viz. It's the problem of just looking at, and I know this wasn't your question, but of looking at the 1.6 is obviously the resolution isn't as good as the red visible, and it's hard to interpret, right? So, you have this obviously dark area where there's a lot of ice crystals. Ice is has lower reflectance in the 1.6, and that's why you're getting that. But yeah, I think we should definitely look at it for sure.
Hey, Chad, this is Mike up in Medford. Thank you for your presentation. I was wondering, we were talking about the other RGB day cloud convection, and it's actually got the word convection in there, which says, hey, maybe this one should be called the convection RGB. And did you look at that one compared to this one? And I know the 1.6 adds everything over the other one, because that just substitutes the 0.64 with the 1.6 here. So did you compare that one to this one? And after using this one for a while in a convective mode, would you ever use day cloud convection?
So I didn't look at it. That's a great idea. I should look at it. So I don't know. I mean, I guess my thought is, so what happened? So this is kind of my thought. So as convection develops, what ends up happening is because the red component is maxed out, all you get is yellow. And in reality, when you have deep convection, the signal is just completely overwhelmed. And I think I have it in the overview actually, and I can show you that. But look at this. See where it says thick upper level ice clouds here on the right? Like all it is like a yellow visible, right? So you can't really get any more information out because the convection is deep enough where there's just nothing else for the RGB to basically do, to provide you. So I think the day cloud convection, what that ends up doing is it almost acts like a pseudo IR, where when you get those really strong updraft pulses, and that's what the RGB kind of signifies, is that updraft pulse turns yellow, and the day cloud or the daytime convection RGB. And that and the Europeans have shown us that that signifies a very strong updraft that is throwing the same concept, throwing those ice crystals up into the upper troposphere and lower stratosphere there. So I think there's probably there's value for both, and I should probably take a look at that. I'll add it to my things to do on a down day, so 2022 probably.
All right, thanks.
Yeah, I'm glad you enjoyed it.
Hey, Chad, this is Dave in Buffalo. How are you?
Hey, good. How's it going, Dave?
Hey, I have a similar question. There is the day snow fog RGB.
Yes.
It seems like with the 0.64 within the day cloud phase distinction product, there might not be much of a reason to use the other RGB. Your thoughts on that? Yeah.
You mean the daytime convective one that you guys don't have, by the way, until you get fixed grid data, but...
No. The day snow fog, it has a 0.87, 1.61,
yeah.
And then a difference product.
Yeah. So...
Is there a good reason to you be using that one as opposed to the one that you're showing today?
Yeah, you're right. I mean, it's really interesting because you can look at this overview example and you can obviously see the difference between, snow and ice here up in the northern plains and where you have low low-level clouds, liquid clouds, and you can see that pretty clearly there. So yeah, I mean, I think a lot of RGBs are like that, though. You can pull out the problem with a couple of them. I honestly don't have a great answer for you. No, we're just because we're still learning this, and I think some people, like Frank, has, and he's told this that he has problems seeing sometimes one RGB over another, and it's probably good. And I know he's an advocate for this, of having a few RGBs, even though they're kind of telling you the same thing, to just have available. So, yeah, it's a great point. I mean, it does a great job here, distinguishing between snow and ice and those low-level liquid clouds for sure, though. Yep.
Yeah, Dave, this is Frank. Just one comment on that. The one downside compared to this product, the Day Snow Fog, is it doesn't include any of the .64, so you don't get that real high resolution to see the details of the little cells that you would using the one Chad just showed.
Yep, that's a great point.
Yeah, and this is Bernie. I'll add just a few additional comments that what you've been talking about and how I see it is we're looking at increasing the contrast to help bring out features. And so all the points you've brought up in terms of what differences do you see and how people perceive them are important, and that's something that should be thought about too. Even the ranges, like you may have a similar combination in another RGB, but the ranges are different. So
yeah.
It will highlight the feature a little bit differently.
And that's a great point, because the nighttime microphysics. No, it's there's two RGBs that have the exact same recipe, except
dust and ash.
Yeah, dust and ash. There it is. I see it now. But the ranges are slightly different. So obviously the ranges are to pull the ash out, and then in the other RGB, the dust RGB, the ranges are there to pull out the dust. So yeah, that's a great point.
Any more questions for Chad? Okay, well, we'll conclude here, and a reminder, at 19Z, Chad will be giving a webinar on the GLM data in the AWIPS, so hopefully we'll talk to you then. Thanks, everybody, and have a great day.